You lead the DVCON 2022 proceeding leading this paper is related to the machine learning as I read from. I will start off with this paper. The machine learning based verification planning methodology using design and verification data. The assertion is that as complexity of the integration of SOC continue to increase, its development time increases significantly, and the verification time does increase even more dramatically. Typically, a verification process, a large number of directed or randomized simulation test cases are generated and as run as a regression form. In a full chip verification environment, this regulation takes significant amount of time to be completed and it could be a critical path in a project schedule. In this paper, we discuss methodology to efficiently managing the regulation and reduce its runtime. We classify test cases in the regulation by using various machine learning algorithms and correlate with the amount of design changes and previously fed simulation result. During this process, we are able to predict failing test cases in early regression stage, otherwise could find them in later regression stage. It gives additional debugging time and eventually help us to reduce total regression time. The proposed methodology is being applied to the latest mobile SoC project. Introduction. As smart devices increasingly provide more features, SoC, as system on a chip, design size, and complexity are also increasing in a very rapid pace. In particular, its verification complexity and the time increases exponentially, while while the development time of the in particular, its verification complexity and the time increases exponentially, while the development time for is rather shortened. Right, while this means that it's becoming increasingly difficult to satisfy the TAT on time. To overcome these challenges, this paper proposes an optimal verification planning methodology and strategy based on data analysis and machine learning. An SoC product is designed and based on a project specification, and a full chip level scenario-based design verification and block IP level functional verification are performed at multiple development stages. As a SoC project progresses, design challenges continue to occur at each development stage, and two main types of design changes exist from the verification perspective. One, increasing design maturity, and two, increasing design instability. To meet the overall development schedule and maintain the design maturity, the completeness of the verification in each development stage is a very short, serious matter. A very serious matter. Very short. Each development stage is a very serious matter. Figure 1 is the amount of total test and the failing test during regression. During during the course of the project, RTL is changed and released multiple times as a result of the design changes. Once new RTL is released, the person responsible for the verification should complete the regression test for verification as soon as possible to prove the integrity of the RTL. The RTL. And since many RTLs may occur and many debugging might be required during the regression test, it would be better verify the cases with a high probability of failure first and debug them reliably related to RTL bugs or other environment bugs. However, unfortunately, a usual variety of tests included in the regression process from for verification are performed and randomly without any priority. Because it is very difficult to predict which test will fail before the regression test is completed, for this reason, the verification engineers are facing new failures almost every day during the entire verification process. Additional figure 1, a new failure occurs every day during the 5 days of regression test for verification. The green lines means the total number of verification tests on the day, and the red bar shows the number of failure tests on that day. The failure found in just before the verification target date not only puts the verification owner in trouble, but also makes the verification quality worse due to the short debugging time. Therefore, finding tests that will fail and verifying the first at the beginning of the verification period is one of the most important factors in reducing the verification period and enhancing the verification quality. In order to find the test includes failure cases that each development stage, the test case should be analyzed and classified as a verification scenario, and a correlation between the failure occurrence rate that the amount of design changes at each development stage also should be analyzed. In this paper, the verification scenario, future level scenarios for design verification test cases are clustered and applied to the deep learning models. And we analyze the correlation uh, between verification scenario and design domain. For example, design hierarchy, power, performance, and specification, and the development stage to confirm if there is actual and meaningful relationship. Background: machine learning, clustering, and classification. Machine learning (ML) is widely used to predict what input data means. Whether the predicted result is right or wrong can be checked by comparing with the actual answer. Machine learning method can be divided into supervised learning and unsupervised learning according to the presence or absence of the correct answers. In this study, verification scenario which will be applied as input to ML models, is too large and various to be labeled directly by humans. So potential labels were obtained through clustering using k-means, and that the ML models were learned using those labels from clustering process as answered. A clustering is a technique of grouping data into several clusters and finding groups of similar clusters. Thus, objects in one group are more relevant than objects in another group. The k-means are one of the clustering techniques. It divides input data into a k-cluster with a high similarity or high relationship depending on the potentially discovered features. Recently, a variety of ML libraries have been provided, so it is not difficult to use k-means, but it is entirely up to the user to find a k-value that controls the clustering result. Fortunately, various methods of obtaining k have already been studied, and elbow and silhouette, which are the most commonly used, were used in this paper. Elbow is most commonly used method using within clusters sum of scalar (WCSS), which explains the uh, vol- total volatility within the cluster, and a cluster with a low score is considered the most suitable k value. Silhouette is a technique that measures how similar an object is to each cluster compared to other cluster. The score ranges from -1 to 1, and a cluster with a high score is considered the most suitable k-value. After obtaining a potential labels through clustering, the label is used to run the classification model. The answer given by the model is called a class. In this paper, we implement a deep learning model using PyTorch in a Python library for convenience of the GPU. Use the flexible code application. The label obtained from the k-means process and verification scenario were used as an input. The train set and the test set considered of A22. And finally, the performance of the 93% correct answer. The machine learning, dimensionality reduction, and PCA. There is a phrase called the curse of the dimension. When dealing with the ML, the number of features can be specified. The object of the analysis is called dimension. As the dimension increases, the possibility of the correlation between each feature increases. Therefore, noise between features increases. Therefore, noise between features increases. Uh, in addition to the high dimension of the data having a lot of noise, the computational complexity required for model learning and analyzing increases exponentially, and the number of necessary data increases in order to distinguish each dimension. To reduce dimensions, experts can analyze data to select unique features or create new features by technology or reducing dimension. Principal component analysis is one of the technology. Principal component analysis (PCA) is a statistical approach that is based on orthogonal information to transform possibly correlated features into a set of linearly unrelated features known as principal components. After transformation through PCA, the first component has the largest possible variance and the second component has the second largest variance under the constraint that is orthogonal to the first component and so on. PCA results into newly extracted vectors that are un, that are on uncor- that are on uncorrelated orthogonal basis set. It is important to note that the PCA is sensitive to the scaling of original features. In this study, we implemented the PCA algorithms using the skitlearn library of the Python software package. 3. Architecture. In this chapter, we describe the architecture of the our data management and analysis system that collect, design, and verification data and build ML models. The SoC design and verification flow. The design and verification of the SoC hardware consists of four processes. The first process is to define the SoC specification. It is followed by the IP development, block development, and the SoC integration processes. IP development carries out in accordance with the SoC development schedule. As an IP development begins, the verification of the IP starts. In addition, a block and where the block is set of the IPs or subsystems is built. The block design and verification include the inter-IP connection with the block. In parallel, connecting those blocks start at SoC or full chip level. In this paper, we define the verification steps for each development stage and define them verification level via in VR1, the IP level design and verification are performed. Block level design and verification, which is verification for a set of the IPs or subsystem, follows. In VR2, IP level design and verification as well as block level design and verification mainly performed. Design and verification full chip SoC design starts. IP level design and verification are complete before the BR3. In BR3 and BR4, design and verification for blocks and full chip SoC are mainly performed. In BR4, a regression, which is batching a larger of test cases for blocks SoC is performed mainly. The verification scenario. In design and verification process of SoC product, test case and the test specification of the verifications are different depending on the specification and the development stage. A verification of each development stage includes verification full chip level functions as well as of each block or IP-level functions. Also, the verification scenario includes the sequence information of the function and register setting information of the related design. Design domain. During design and verification of SOC, various types of data exist. We categorize our design into 25 specification areas such as a bus interface, register, ports, and etc., which is called a metadata design domain. In order to analyze the various types of the design and verification data, we collected three types of data. The first type is verification data, for example, verification code changing. The second is the metadata of design, for example, IP exact component. And the third one is the design data, for example, RTL changes. Okay, we collect the changed information for those 25 representative metadata for specification. 25 specification areas. Okay, the design data analytics (DDA) and the design verification automation system (DVA). Figure 2. Whereas Figure 2, the overall architecture of experimental design system DVA and the DDA. Okay, the Figure 2 shows the system that is configured to apply the experimental flow to each development stage of SOC project. During an entire SOC system, design and verification data released almost every week with a name, called a label from the design repository. The design data include registers, integration information, and the RTL of each one. The verification data during the verification process also changed also every week. In this development stages, numerous data are generated, deleted, and changed. To manage such a large quantity of these data, we have developed a system called DDA, which collects and analyzes those changes data in each design domain. Figure 2 shows the three modules of data types supported by DDA, although more types of data are generated and covered in the SOC development process. We also have developed another system called DVA that is originally used for collecting verification scenarios data and managing the regression runs at each development stage. In particular, DVA uses the regression manager to collect all verification data, for example, LSS information, range result, and run logs environment. We add the verification and the triage scenario planner based on the ML cluster and classification model and the original DVA system. Changing and in each changes data in each design domain analyzed by DBA, and verification scenarios data analyzed by DVAs are used as the training data of the ML model. In this paper, 1.7 million of simulation results from verification scenario through DVR and 4.2 million design files through DDA were used. Used what? In this paper. And the overall architecture of the experimental result is a design level weak label 12225. DDA, data transfer detector, DDA, verification data change detector, fine change library changes, test option changes, design meta change detector, expect IRKS changes, design RTL change detector, plug changes, IP change, glue changes, automated regression changes, data cluster and classification, verification strategy scenario planner, regression manager, dashboard, report system. The verification planning methodology. Change RTL as a target verification are bound to affect the verification scenarios, but it is not common to analyze the correlation between the design and verification because the design and verification are usually conducted by a separate organization. However, we analyzed correlation based on the following three assumptions. As mentioned in the background above, the verification scenario includes various design information and simulation conditions or options. We classified a certain verification scenario based on these options. Second, two is any RTL changes would affect the result. Three, by analyzing the correlation between one and two, we reorder the dispatching the priority of the verification scenarios during the regulation run at each development stage, which should reduce the total regulation time, runtime, or increase verification completeness quicker. ML-based scenarios clustering and classification. In order to analyze the relationship between the verification scenarios and the design domains, it's necessary to identify the characteristics of each verification scenario and cluster the verification scenarios according to the characteristics. The data prepared for clustering includes millions of verification scenarios obtained from the 5SC project. Oh, really? The best quality clustering method would be for a person to identify the composition of the verification scenarios and specify what characteristics it has. What is it? Clustering. However, because the amount of verification scenarios is too large and varies to be classified manually, clustering through the k-means is performed. When analyzing the regression data, the first challenge we faced is that the number of features to analyze is too large. Since reducing the number of features in dimension is essential to achieve the high performance of the ML models, we used sklearn's Cornell PCA to reduce the dimension for steering as a nonlinear data. By checking the cumulative contribution rate, and the feature count is reduced to 100. The experimental result of the elbow and silhouette method. The number of the cluster The number of the clusters to classify our verification scenario is determined based on the experimental result of the elbow silhouette method. In Figure 3, the result of the elbow show that the large number of classes, the number, the smaller the value of SSE, some square error. However, when a model is actually trained with more than 60 classes, its performance tends to be rather poor. Therefore, the range of the number of classes fixed from 40 to 60 through elbow. The experimental result is additionally performed with the silhouette method. Finally, it is determined that the number of clusters for deep learning model is 47, project A and B, and only 44 classes are valid. Figure 4 is a comparison result of the pass-fail case classified ML model. Figure 4 is the result of classification into a model as trained to with the same regression for two SOC projects, project A and B. Since the regression run generally start at a VR3 stage, the VR3 stage result of the two projects are compared to ensure that the verification scenario for the regression is well classified. The result of the clustering and the classification are considered reliable, and the trend of each class of the different projects are similar. The project subsequent process is analyzed project A, and since the verification scenario data are A, where steps used. The figure 5 will failure the verification stage and class. Analyzing verification scenario fell with the development stage. By classing the verification scenarios of all development steps of the SOC project through a model prepared above, the result in Figure 5 can be obtained. And it shows the failure rate of each class and the development stage. For example, more failures occurs in class 2 and 43 and 44 in VR2, and class 1 and 38 and 41 in VR3, and class 19 and 21 and 29 in VR4 respectively. As class is checked early in each stage, in the development stage, failures can be found more quickly. Figure 6 is changed the RTL and the total RTL with the design domain and stage. Analysis of the design domain changed by a development stage. As shown in Figure 6, The RT change trend according to the VL stage differed for each design domain. Most specifications tend to converge from VL2 and VL4, but some specifications tend to differ. In addition, some specifications are stable with a little change from a VL2, which is an early stage of development. What stands out is that in the case of the spec 4, 8, 14, 16, 22, and 25, such as both interface and port and register, can be as it can be seen that the amount of changes is higher in VL4 than VL3, and this way each specification shows its own trend in development stage and provide a guide to check whether such trend affected the regression learn result. Correlation between design domain changes to verification scenarios, and a correlation between the design domain changes and the verification scenarios. So, based on the result of the previous steps, the correlation between the changes by design domain and the verification scenarios is analyzed. As figure 7 shows, changes in spec 9 and spec 19 and spec 21, such as the component instance register, uh, component instance and register, right? Is a cause failure in most classes. Especially class 2 and 43 and 44 that had many failures in field 2 stage are sensitive to almost all design domain changes. Note that the amount of changes for spec 4 and 6 and 16, such as bus and port, is inversely correlated with fail, and thus this specific change rather affected the direction of a stabilizing RTL. Using this RTL, a correlation table, we choose the job dispatching ordering of verification scenarios in regression. For result, the experimental result used in this paper at this study has been applied to the flagship mobile SoC, and the efficiency can be measured from the full chip SoC level application. Based on the data from the verification regression for early for each development stage, a scoring by the considering failures and the design change for each class were used in the reordered regression schedule with a specific class based on those scores are shown in Figure 8. Run order. Figure 8 run order regression schedule with the classes. Figure 9 is comparison of the failures between real optimized verification scenario. Based on scoring result, verification schedule is optimized and compared with the existing verification result. If the verification plan for each class is optimized, the failure cases occur early, and thus debugging time is reduced and the pass rate can be raised quickly. Figure 9 shows that verification time for each failure rate is 70%, 6 days optimal versus 10 days original. 80% 8 days optimal versus 11 days original. 90% is 10 days optimal versus 12 days original. The result is a verification stability that can be secured only by changing the order of the execution of the test case based on the scores. The verification period of each labels and the VL3 stage from 13 to 15 days. Rapid securing of the debugging time and the pass rate of the 4 to 2 days can improve the process rate of the verification functional pass rate by 21.5% up to 80% of the VL3, which is 64% of the total verification period. And it confirms that the debugging time, that is switching period from class to pass, which has a critical effect of the test optimized in actual VL3, takes 1.3 days for the median value, 1.9 days of the average value, and 14 days for debugging period occurs. Conclusion. In this study, we've analyzed the correlation between the design changes and the verification scenario using the machine learning. Based on this analysis, we developed a method to optimize the scheduled verification jobs or a batch of the test cases. This helps us to reorder the set of the verification scenarios during the regression. Run would be failing verification scenarios earlier than the others, and then the act eventually save our verification time. To achieve this, we train and build our ML model using the verification scenarios of five SOC projects, failures pattern from two SOCs, and the design changes in which data in each development stage from the one generation old SOC. Using this model, the verification of job scheduling is optimized for the current SOC project. We have several interesting observations. Uh, uh, throughout all SOC projects, every design domain has a similar failing patterns for a given development stage. This means that the failing cases and their failing time could be predicted for a chosen design domain, which would help preparing our verification planning in advance. Another observation is that a change of some domain a design domains cause more failing test cases while the other decrease failing test cases. For example, the changes on the design domain such as bus interfaces or approach tend made a more ma- tend to made tend tend to make more test cases passing, while changes on design domain such as register tend to cause more test case failing. This also gives some hint to prepare our verification planning for given design changes. Our analysis methodology and system still have several areas to be improved. It is required to correct and preserve the data or development stages of or a major associate project to build a better ML model, to refine our ML model to predict our verification status more accurate. Code and functional coverage information would be required to incorporate in our analysis. This might give more precise root cause or failing test cases. It would be greatly reduce our debugging time and total verification time. Reference: expediting the design bug discovery regulation of x86 processors using machine learning AMD 2021. And accelerating SSL verification using process automation integration 2020 DVCON 2020. Performance analysis of PCA, sparse PCA, corner PCA, and incremental PCA algorithm for heart failure prediction. Face recognition using principal component analysis. International Conference of Computer Vision and Pattern Recognitions in 1996. The monitoring of processes of multiple operating modes through multiple principal component analysis model. Industrial and engineering chemistry result 2004. Thank you for your time.